I want to illustrate this by some examples, and these examples have to do with extremal problems for H-colored graphs and their applications. Okay, so since I would be talking about H-colored graphs, let me give you a definition which would be crucial. So I have a graph, right, and the edges of this graph are colored, and the coloring is called proper if at every vertex we have edges of all different colors. Now, this is a very central notion in graph theory, very extensively studied, but if you see it first time, maybe one example which you should keep in mind for this talk is the following example, which actually would be interested broadly to various areas of math, is a Cayley sum graph. So imagine that you have your favorite group and some subset of elements of this group. Then I can define you the following graph. So the vertices of the graph would be elements of the group. And so I'll write this operation in the group with plus, but it doesn't need to be abelian. And I connect two vertices x and y by an h if x plus y equals some element of this set S, right? Now this is a symmetric relationship, so it definitely defines your graph. And observe that this graph already comes colored because I can assign to the edge xy the color, this element S. So this element S would serve as a color of the edge x plus y, right? I don't have multi-edges. Now, most of the people probably familiar with the usual Cayley graph where I actually need to take the x minus y equals to S, but then I would need to require that my S to be symmetric, will contain element. It's an inverse. It would be very related notion, but it's much more convenient to work with the sum graphs, right? So again, you have a group, bunch of elements, x plus y equal to the elements gives you an edge, and observe that moreover this edge already can be colored by an element of S, and this is a proper coloring because x plus y and x plus y1, it's two different numbers, so you not repeat color at the vertex. Okay. So as the title suggests, I want to talk about restriction, restricted subgraph in H-colored graphs. So let me talk about the restriction. So I will look on my big graph, which is properly H-colored, and I want to find inside some structure, some subgraph, which is well organized. And what would be well organized? I will have certain restriction on the coloring of the edges of the subgraph. Now, one natural restriction would be that some colors appear uniquely. So they appear only once on the subgraph. Or even more generally, all colors appear uniquely. Right? In this case, I will call a subgraph rainbow. Right? A subgraph of a graph is rainbow if all edges of the subgraph got distinct colors. So for example, on this picture, the sixth cycle is rainbow. Okay? And so what I will want to do in this talk, I want to discuss generally this question. So if you have a large and dense graph, okay, and then you look on the arbitrary proper edge coloring. So this would be important. I'm not taking any specific edge coloring. The only thing I want from edge coloring is that it's proper, that at every vertex all edges get distinct color. I want a very general result which says that if my graph is sufficiently dense and large, I can find in such a coloring some copy of a fixed graph H, your favorite fixed graph H, which say is rainbow. And then I'll show you that this type of problems appear naturally, not necessarily only in combinatorics, but in other areas of math. Of course, I will just take the problems from these other areas and I rephrase them and I'll show that certain results that we prove in combinatorics can be useful. But first, let me make some historical remarks. Actually, yes?
Just to parse this, so rainbow copy of certain structure means that H is not colored itself.
No, H lives in G. So for example, so in this structure up there, there would be no rainbow cycle, and actually it would be a good example. So it's a cube colored properly, and observe there is no rainbow cycle because on every cycle in this graph, every color appears even number of times, right?
I'm referring to the question with the structure H.
Right, so H would be a subgraph of a big graph. So I want to look on this graph, and I want to say find the fourth cycle, but in such a way that all the edges of this fourth cycle got distinct color. And in this picture, for example, there is no one, right? So I would not be able, so the top picture does not contain a fourth cycle where all edges get distinct color. So if you look on 4 cycles up there, every color appears twice, right? So like what I want, for example, if I have, blue edge and then another blue edge and then maybe red edge and green edge and another blue edge. For example, this triangle, which I got, so this is my graph, and this is a subgraph of this graph, and this triangle is rainbow. All edges are distinct. And I would be interested to find such substructures, and they will have certain mathematical meaning, and I would want to have certain general theorems which says if my graph is large enough and rich enough, that no matter how you color its edges properly, I always find such a substructure.
Any H, I'm just asking.
No. H would be also specific to the problem, right? So a big graph would be given, the H would be also given, and H would be specific to the problem, right? Definitely not average, of course.
Because the H is separate and uncolored, and we want to have a
Right. H is uncolored, it's lives somewhere, then I want to find its copy, but not just an arbitrary copy, but the copy where the colors do not repeat itself much. Okay, and we'll see in a minute. Very good. So more questions. Please do ask. So the history of this problem goes back more than 200 years to great Leonhard Euler and his study of Latin squares. Now, what is a Latin squares? I think we all know. So you have n by n square. You fill every square with a number, so that every row should contain numbers 1 up to n. Every column should contain numbers 1 up to n, right? And in every row and in every column, the numbers should distinct, and you get a Latin square. Latin squares are very natural objects. So, for example, you immediately get Latin square if you take finite group and you take it multiplication table. If you like Sudoku, when you fill Sudoku, you get again a Latin square. But they appear naturally also in design theory, in finite projective planes, error-correcting codes, two-dimensional permutation, to name few. Now, a very important object related to Latin square is a transversal. Now, what is a transversal? So you want in Latin square to choose a generalized diagonal, means bunch of squares, no 2 in the same row, no 2 in the same column. But in addition, you want this 5, so this was 5 by 5, 5 squares to contain all numbers from 1 up to 5. So this is called transversal. Is it clear? Right, so no 2 in the same row, no 2 in the same column, and containing all the numbers. So actually what Euler asked in 1780 is for which n you can have an n by n Latin square. So you can create a square, but your Latin square should have a property that I can decompose it to the n transversals, right? Total n square entries. Every transversal is n. All the numbers appear n times. So potentially it's possible. So can you do it? Actually, it's a very cool story behind this problem. So at that time, Euler was living in Russia, working for the Russian Academy of Science. The queen, actually not a king, queen back then was Catherine the Great. And there was a puzzle which was circulated at the court of Catherine the Great, which was exactly, so it was talking about officers from 6 different regiments with 6 different ranks, which you need to arrange certain way. And the solution for this problem was exactly this. Do you have a 6 by 6 Latin square which can be decomposed into 6 transversals? So that's how Euler got interested in this problem, right? And so here's an example. So I cannot do this for 6. We will talk about this in a minute, but I can do it for 5. So here is a 5 by 5 Latin square, which in addition is decomposed into 5 transversals, right? Because you can see, you can check every color contain 1 element at every row and every column, and inside this square there are all different numbers. Now actually there is another cool way to say this problem. What Euler actually was interested, it's so-called a pair of orthogonal Latin squares. So imagine you have 2 Latin squares of the same size, m by n, and now you want to superimpose them. So if you put one on top of another, then every square will contain a pair of numbers. And then the Latin squares are called orthogonal if all these n square pairs are distinct, right? So potentially you get n square pairs. So if I can get them all distinct, then such Latin squares are orthogonal. And what you can show, I will show you in a second, that if you have a Latin square which can be decomposed into disjoint transversals, you can create another Latin square which is orthogonal to it, right? So here is my example. So here is a Latin square which was decomposed to all transversal. Now I take the first transversal, right? This was the green one, but now instead of numbers from 1 up to 5, I'll write only 1. But observe, I am totally legitimate because it's 1 appears in every row and every column only once. Then I take the second one, yellow, and I put only the numbers 2. And then the third one, purple, the number 3, and then blue, the numbers 4, and then the white one, the numbers 5. And now observe that when you put this transversal one on top of another, you indeed get all 25 pairs. So it's an equivalent problem. Okay, so this was the history, but how this related to graph colorings. So the thing to observe that if you have a Latin square, and on purpose didn't put numbers, but they put colors inside, I can think about the Latin square as the edge coloring of the complete bipartite graph. So you see at the bottom I put the rows, on the top I put the columns. Every square, for example B3, corresponds to the edge which connects point B with point 3. And the color of the square corresponds to the color of this edge. So therefore, for example, these red squares give me these colors. And similarly, you can color the complete bipartite graph. Is this clear? This is really important. And the thing to notice that this coloring is proper, because at vertex A, I got this row and they're all distinct colors. At vertex 1, I got this column and they're all distinct colors. And now the important thing to note is that if you take a transversal, maybe not necessarily full transversal, but just squares of different color in different rows and columns, to what it corresponds. Because they stand in different rows and columns, they correspond to disjoint edges. And so therefore what you get a rainbow matching, right? So the transversal, not necessarily full, corresponds to collection of disjoint edges, squares in a different row and columns. So they don't share the top vertex, they don't share the bottom vertex, and moreover, they different colors. So therefore, the equation of Euler, I could have said is as follows. Can you construct me a complete bipartite graph, n by n vertices, all edges present, with a proper coloring in n colors, in such a way that I can decompose its edges into n rainbow matchings, right? And here, it's exactly what I mean. My graph H would be a full matching and disjoint edges, right? And I want it rainbow. And not only I want one, I want to decompose everything, okay? Good. So the equation of Euler took 180 years to answer. Actually, as you remember, the equation n equals 6 was the equation which came from Catherine the Great, and Euler didn't manage to construct this square because indeed it does not exist. So one can show that there is no 6 by 6, so this officer's problem has no solution. So there is no 6 by 6 Latin square which can be decomposed to disjoint transversals. But then Euler, by mistake, thought that it's a quality of the, it's a property of the number. So if your n is 2 mod 4, you never get a Latin square which can be decomposed into disjoint union of transversals. But he was wrong, and his conjecture was disproved by Boyce, Parker, and Shrikande in 1959. Actually, it's very interesting. When they solve it, this event, this solution, make front page of New York Times. You can Google it and you can find New York Times with these names and the picture. Okay, to finish the story of Latin squares, I want to talk about recent spectacular result by Richard Montgomery. So observe that in this top square, Latin square, so it's an example of Latin square, you can check that it doesn't have a full transversal. So I found 3 elements in different rows, column, in different colors, but I cannot find 4. And therefore, it is a natural question. If I give you a general Latin square, how big a transversal you can find? And it appears there is an old conjecture from the 60s that this missing one is as bad as it gets, right? So you can always find in Latin square, n by n, a transversal of size n minus 1. And indeed, very recently, in spectacular work, this was proved by Richard Montgomery. So he proved that if n is large enough, then every Latin square has a transversals of size n minus 1. So this question is even quite difficult, even if you look on multiplication table of the finite group. So there was another very famous conjecture called whole page conjecture, which was put in 50s and solved only recently, which tells you when a multiplication table of finite group has a transversal, and it was only solved using classification of finite simple groups. So even in group theoretic setting, it's a difficult question. So he gets n from his proof, but it's a big number, right? It's not small. Okay. So now I want to go back to this problem of finding subgraph with restricted coloring. And so let me start with the most simplest object in graph theory, that of a cycle, right? So the cycle, right, I had it on the board, right, is just these two regular subgraphs. So this is a cycle. It's the most basic concept in graph theory. And the most basic result with respect to the cycle says that if you have graph on n vertices and n edges, it should contain a cycle. It cannot be acyclic. Now, the natural thing which I want to ask, suppose I have now H-colored graph, properly H-colored graph, and I want to find a cycle, but with certain restriction. And as I said, the restriction would be on the uniqueness of the color. So let's take the most basic restriction. I have a graph, properly H-colored. I want to find any cycle. I don't tell you the length, I don't care. But I want that this cycle will have at least one edge of unique color, which means this color does not appear anywhere else on the cycle. So how many edges I need? So I want a statement that if graph has many edges, properly colored, that it contains a cycle with unique color. Now observe that this question already quite interesting because the answer for this question stopped being linear. So this was my question. So the answer for this question is stop being linear, and here is an example. It's actually the graph which I had before. This is a binary cube. So you see what you can do? You can take a group z2 to the k, right? So all binary vectors of length k, and define a Cayley sum graph of this group with respect to standard basis. So what it means, the vertices are binary vectors, and two vectors are adjacent if u plus v equals ei, and moreover, in this case, I color this edge by color I. So I immediately get this binary cube, which you have upstairs, which is properly colored. We said every Cayley sum graph comes properly colored. And there are two things to observe here. So first of all, observe that the cycles in this graph, they all have every color even number of times, because cycle corresponds walking along the direction of the standard basis. And in order, because standard bases are linearly independent vectors, in order to come back, you need to cancel every vector. So you need to have every vector even number of times. Addition modulo 2, only if it's independent vector, cancels if vectors appears 2 times, 4 times, and so on. So every cycle, and indeed you'll see, you can check, that every cycle here will have every color 2 times. So you don't have any cycle, no matter what length, with unique color. Moreover, observe that the number of edges is roughly n log n, because the number of vertices is 2 to the k, which is my n. The number of edges is the degree of every vertex is k, because there are k standard bases. So the number of edges is k times 2 to the k minus 1, which is half n log n. So I need at least n log n edges, unlike the trivial result from graph theory, to guarantee a cycle with some edge of unique color. Even one edge of unique color is not easy to get. Now we look, so we look on this problem about 20 years ago with Peter Kivas, Dhruv Mumbai, and Jacques Verstraete, and we proved a complementary result. saying that n log n is an answer for this problem. So actually what we proved that if you have a n-vertex graph with roughly twice n log n edges, then no matter how you properly colored, and again, this is a theme. I don't control the coloring. Coloring comes from you, right, from adversary. No matter how you color this graph properly, as long as it's a proper coloring, it always contains a cycle, actually even a cycle of logarithmic lengths, which has an edge of unique color. Okay? The proof actually is not very difficult, so what you can do is, because the coloring is proper, you can color rainbow paths of the length roughly log n, and then you can show that there are so many of them, and you have only n square vertices, that there would be two vertices, and between them there would be two rainbow paths where the colors of this path are not the same. And obviously, union of two rainbow paths which don't agree on all the colors, since every path is rainbow, gives you a cycle with unique color. Okay? Now, what I want now to put it in the general mathematical constant and show you that already this simple result have some interesting applications. So for that, I need a notion of even cover. So what is an even cover? So imagine you have a collection of sets on some vertex set, and you want to find a sub-collection, a bunch of sets, which cover every vertex even number of times. An alternative way to think about it, think that for every vector you take, for every set you take a binary vector, which is a characteristic vector of the set. It has ones on the elements of the set and 0 everywhere else. Now, even cover means that the sum of these characteristic vectors is 0 modulo 2. Or if you think in terms of coding theory, that there is a linear dependence between these vectors, okay? So even covers are very natural objects. So observe that, for example, a cycle is even cover, right? Because if I take these sets of size 2, every vertex covered 2 times, so it's even cover. Now, if you have a system of linear equations and you're trying to solve, observe that in particular you're trying to see which linear equations are dependent, and dependent equations are exactly form an even cover. If you add them, they add up to 0 mod 2. So therefore, it's a natural equation if I give you a collection of sets. Let's say all my sets have the same size, k, and I give you m sets, how small even cover you can find, right? So I give you the number of sets, you know their size, how small is an even cover? Now, this is a very central question also in graph theory because, for example, even in the case that the sets are of size 2, it's a very famous question that if I give you a graph and I tell you the number of edges, what is the shortest cycle you can find? It's called Gauss problem. It's a very old question. Another important question in the coding theory, right? You can think about these sets of size k as a vectors, binary vectors with precisely k1s. And then I'm telling you, if you have this, if you take a linear subspace spanned by this set of vectors, what is the shortest linear dependence in this subspace? Or what is the shortest word in your code? So the linear subspace in the language of coding theory is just a linear code. So what is the shortest vector in this code? It's called rate versus distance trade-off. So, right, so you can phrase this question in this language. Very good. So about 15 years ago, Uri Feige was interested in this question, and he put forward a precise conjecture. He said that if you want to find a linear dependence roughly of length L, then you need to have n times n over L to the power k over 2 minus 1 vectors, right? So you have vectors with precisely k1s. And, right, so observe, for example, just a sanity check, right? So if k equals 2, then 2 divided by 2 is 1, 1 minus 1 is 0, so you need only linearly many sets, and we know that if you have n edges, you have a cycle, right? So in the case k equals 2, this is a trivial statement. So the interesting statement when k is large. So the reason why Feige was motivated by this thing, so first of all, it's a tight statement. You can take your collection of m sets of size k at random, and then you can see that you cannot improve this result. So this result gives you an answer because you have a construction which shows that it cannot be improved. And also this thing appears naturally in computer science. So for example, if you have a random instance of computer science problem and you ask, is there, right, and say satisfiability for people who know what satisfiability. So you have a random set and you want to persuade me that this set is not satisfiable. Is there at least a small certificate which you can show me, which will show that the set is not satisfiable? These questions appear there. Okay? So this conjecture was solved up to a logarithmic factor recently by Guruswamy, Kothari, and Monohar. But their solution was quite complicated. So despite that it's a combinatorial problem, it used tools from random matrix theory, something called non-commutative Hinchian inequality for spectra of random matrices. And so what I want to do today, I want to show you that looking on this problem in perspective of this H-colored graph with restriction can give you a very short solution for this problem. So what we are going to prove, it's some joint result which I got with Hassier, Kothari, Mohanty, and my PhD student, David Correa. So where we're showing that this conjecture of Feige is true if we add a one logarithmic factor, right? So if you have n times n over L to the power k over 2 minus 1 log n k subsets on n element set, we have a short linear dependence or short even cover. Now, the numbers not important. Don't pay attention too much to the numbers. Let me show you just one slide. So you can write this whole proof in one slide, at least in the case where k is even. And you will see why it's natural to look on this problem as a problem about H-colored graphs. Okay? So any questions? So again, just because that's maybe the nicest thing which I'm going to show in the only proof. So again, you have vectors. Every vector is binary, has precisely k ones. You give me a bunch of them. And I want to claim that if you give me roughly n times n over L to the power k over 2 minus 1, then I can find roughly L of them up to logs, which sum up to 0. Right? So then there is a short linear dependence. Okay. So actually, let me do one more simplifying thing. Let me take a very specific k. You'll see that the proof easily generalized. Let me take, I said k even, let me take k equals 4. That would already illustrate all the ideas. So L is some number, right? So you tell me what dependence, how short dependence you want. For example, you can take your L constant, and then it will tell you that if you have n times n to the power k over 2 minus 1, total n to the power k over 2, then you will have a logarithmically short dependence. Right? Already that's highly non-trivial if you try to do it, right? So imagine in my case k equals to 4, I want to say that if you have n square vectors with 4 ones, then even epsilon, even n squared divided by billion, then you will have a logarithmically short dependence. You can find log n, constant log n vectors, which sum up to 0 mod 2. Right? So that's, for example, a thing to think, right? N square over billion vectors with 4 ones each will have logarithmically short dependence. Right? L you can choose. So that's why this result is general. Depends. Okay. Good. So as I said, let's start. If you're doing it for k equals to 4, then your statement is you have n squared divided by n log n sets of size 4, or vectors with precisely 4 ones, and you want to show that there is a short linear dependence. So how I do this? So I take a new graph G, right? And the vertices of this graph would be all L element subsets of my universe, right? So basically, so instead of vectors with the 4 ones, I take the vectors which have L ones and everywhere else 0, right? All possible such vectors. So these are my sets, right? And now I need to define the graph on them. And the graph on them would be already very familiar to you, Cayley sum graph. So what I'll do, I'll say two sets S and T are connected if when you add their characteristic vectors, you get one of these 4 tuples from your family. right? So S is connected to E if Vs plus Vt equals V. Or if you want a picture, S is connected to T if they have intersection of size L minus 2, and S contains 2 elements of your H, and T contains 2 elements of the H, right? So they basically, the symmetric difference give you these 4 elements, right? But it's much easier to think about as this graph, right? You take this vector plus this vector, these vectors with precisely L1s, and their sum modulo 2 is this photopole, okay? So this is your graph. Now observe that this graph already comes colored, and I color the edge between S and T by color E, exactly like I do in some Cayley sum graph, okay? Now, another thing to observe that this coloring is proper, because this is a question. So if you tell me S, vertex S, and you tell me the color E, I immediately know to what it is connected, right? Because I can solve this equation. I can write Vt equals Vs plus V. So at every vertex, there is only one edge of every color.
So the number of V's is n choose 4.
Yes, yes, yes. Very good. So now let's do the computation. No, the number of V's is n choose L, because for every subset of size L, there is a set, right? So the number of vertices in the graph is n choose L, because for every S of size L, there is a vertex. So this is n choose L. Now let's count the number of edges. So the number of edges is the number of my photopoles times the sets of size L minus 2, because for every edge I can think, I took a photopole, I split it into 2 pieces of 2 vertices, add the set of size L minus 2, this was one edge, this was another edge. Now what I spare, I will not do the computation, but the numbers are cooked so that you see, I can check that this expression is precisely twice n log n. And now you remember this previous lemma. So I told you, if you take arbitrary graph on n vertices with twice n log n edges, which is properly colored, it should have a cycle with unique color. Okay? So let's take such a cycle with unique color. So there is k sets of size L, S1 up to Sk, which form a cycle, which means if you add 2 consecutive vectors, VSI, VSI plus 1, you get a photopole, one of your photopoles. And moreover, some of the photopole appears only once. Now what you can do, you can take these equations and start adding them. And observe that this every vector VSI will appear twice, VSI plus VSI plus 1, and also you will have VSI plus VSI minus 1, because it's a cycle. So if you add all these equations, because you're adding modulo 2, this thing cancels out, you get 0. And therefore here you get your sets of size 4, which you add modulo 2, which equals to 0. But now you know that this is a non-trivial linear combination, because 1 EI appear uniquely, so they cannot cancel out. It cannot be that they come in pairs, right? So the fact that there was a unique color says there was a EI which would not be canceled out with anybody. It's a unique set, appears only 1. And moreover, we know that the length of the cycles is log base 2 of n, which is exactly L log n, right? So it shows you that this simple lemma can be used to answer some question, right, and appears naturally. As I said, if you think about it, it's indeed built to kind of, in this question, to think about H-colored graph and Cayley sum graph. Any questions? Okay. Let me go forward. So also about 20 years ago, together with Peter, Dhruv, and Jacques, we asked more general question. Okay, so if I want a cycle where H has unique color, then you need n log n edges, and we know that n log n edges are enough. But we actually conjectured that n log n edges are even enough if you want a totally rainbow cycle, right? The cycle where all edges get distinct colors, right? So this is a question. Despite that innocently looking conjecture, this problem still is open. We don't know how to solve it, but we know to get some results which suggest that the conjecture is probably true. The first result which I want to mention is a result which I proved with Oliver Janzer, which says that if you have n log n edges, then you can get almost rainbow cycle, right? Before I showed you that you can get a cycle where one color is unique. Now this theorem says you can get a cycle where almost all edges is unique. Only epsilon fraction of edges repeats the colors. Not quite rainbow, but mostly rainbow. This is the first result. The second result was very nice result, which was recently proved by Alon, Bukic, Sauerman, Zakharov, and Zamir, which shows that if you take this n log n and add to it tiny bit, log n, right, even a more diminishing fraction, then the statement already is true. So if you have graph with n times log n edges, and it's properly colored, then it contains a rainbow cycle, okay? So this is a statement. So roughly n log n edges is already enough to get a rainbow cycle. Now let me again put this question about rainbow cycle into perspective of other areas to show why it's useful. So what I want to talk now about is additive combinatorics. So again, imagine you have your favorite group, and then a subset of elements of the group is called dissociated if any linear combination, again, I'm not assuming my group is abelian, but it's convenient for me to write it as a plus, any linear combination of the elements of S with signs plus 1 and minus 1 or 0, right? So you take just some subset, some with plus, some with minus, right, cannot give you a 0, right? So basically, if you only use these coefficients, this collection of elements of your group is independent, right? So if you look at it, it's very much immediately should remind you, you know what we know from linear algebra, the notion of basis. And indeed, you can think about dissociated sets as some analog of basis in vector spaces, but here we don't have field, right? We just have elements of the group. So we know that if you just add them and subtract them, you cannot get 0. So this is a dissociated set. Now, these sets appear very naturally in harmonic analysis and additive number theory, and they're very similar, indeed, as I said, as an independent set in vector spaces in the following sense. So first of all maximal dissociated sets in the groups are spanning, so you can represent any other element of combination of the elements of the set just with a coefficient plus minus 1, just by adding and subtracting them. And moreover, you can show that maximal dissociated sets have roughly similar size. And therefore, this motivates the following definition of dimension, right? If you have a group and you have a subset of the group, then the dimension of the subset is just a size of the maximal dissociated set this A contains, right? So kind of if it would have been a subset of a vector space, then it just would be the largest independent collection of vectors which contains, but again, we're in the group, so this is what makes sense. Very good. So this is the notion. And now, one central theme in additive combinatorics is study of sets with small doubling. So what I mean by this, so imagine you have a subset in the group, A, right? A is a subset of your group. And then you know that if you take A plus A, that the size of A plus A is not much bigger, right, than the size of the set you started with. Of course, if set had n elements, you can get almost n square elements. But for example, if you take an arithmetic progression and add it to itself, it goes only by a factor of 2. So in additive combinatorics, people want to study the sets where under addition do not grow. So now the intuition is that if set under addition doesn't grow, that it behaves something like a subspace in a vector space or subgroup in the group. And one way to kind of make this precise was in the following theorem. So suppose you have a subset in the group gamma such that A plus A is not much bigger than the size of the original space. Then I want to say that this set close to a subspace, right? So now if it would have been subspace, say it's over GF2, then its dimension should have been logarithmic. And that's indeed what people proved. So you can prove that if you, in a abelian group, and you have a subset of abelian group which doesn't grow under addition, then the size of the largest dissociated set in this subset of A has logarithmic size, at most logarithmic size. And if your group is not abelian, the conjecture is that you can get still logarithmic, but we cannot prove it. We can prove it almost logarithmic, so log to the power 1 plus little o 1, okay? So is it clear, right? So you have a subset of the group, under addition it doesn't grow, then the claims that dimension, the size of the largest dissociated subset which it contains, is only logarithmic. And the proof uses, the original proofs were different, but the proofs which one can give uses these results about cycles in H-colored graph. So actually, to prove the first result, you can use a simple lemma which says that if you have n log n edges and you properly colored, then you have a cycle with uniquely colored edge. And to prove non-abelian version, you need a stronger result about rainbow cycle, which was proved by Alon, Bukic, Sauerman, Zakharov, and Zambir. Okay? So this is another interesting setting in which this result appears. Any questions? Huh? Sorry?
Stupid question. What's log of 1 plus O of 1 A?
So this is actually this log times log log, right? It just, I wanted to write it shortly, right? So it's a log of A times log log of A, right?
So it's not
Yeah, yeah. It's almost log, because as I said, if I would have knew this conjecture that whenever I have n log n edges, the rainbow cycle appear, I would have log. Right? It just really, you can, and again, the proofs are one page, but I just want to save time. It's really very interesting how, right, the people in additive number theory think about this question before, but it's really appears one-to-one correspondence with this rainbow cycle problem. Okay. So now I want to change gears. So far I talk about matching cycles. Now I want to talk a little bit about trees. Right, let me remind you, tree is a connected graph which has no cycle, right? That's why we call it tree. It indeed looks like a tree, right? Just a connected graph with no cycles, okay? So for the results which I'm going to present, I need to relax a little bit edge coloring. So instead of looking on proper edge coloring, so observe that proper edge coloring at every vertex had every color at most one. I now allow you at every vertex to have every color, say, fixed number of times. 2 or 3, or k. But think about this k is small. K is constant. K is like really small number. So a k-bounded coloring is a edge coloring of the graph, where at every vertex, every color appears k times. Actually, in this talk, I will use only proper coloring or 2-bounded coloring. So I want just also to consider the case where this k equals to 2. Okay? And so what I want to discuss now, right, so we said 1-bounded coloring is just a proper coloring, right? And I want to discuss the following thing. No, in graphs I don't allow. So my graphs are really simple graphs, no self-loops, no parallel edges. So I want to say, now it's a very simple graph I'm going to color, a complete graph on n vertices. So n vertices, all edges are present, so there is no richness in the structure here, but the richness comes from coloring. Now I color the edges of this complete graph, or you color this for me, say properly, or maybe 2-bounded. And what I want to ask, which rainbow trees, I can find the copy rainbow, right? This is exactly the question you ask. So the tree maybe would be given to me by you, but my task would be to find this tree in this coloring. Again, the coloring is adversarial. Tree you're also giving to me, but I need to find this tree such that all edges of this tree get distinct colors. Okay. And before I'll tell you the result, let me give you some motivation why it might be interesting to consider this problem. So the first result which I want to mention on motivation come from the area of graph labeling. Now what is graph labeling? You have a graph and you have a group, and a labeling scheme means to assign to every vertex of the graph some element from the group in such a way that this scheme, this labeling satisfies certain condition. It's a very big area, lots of result, and motivation typically comes either from coding theory or from constructing various networks with interesting properties. So in particular, labeling scheme which I want to talk about is called harmonious labeling, was introduced by Graham and Sloan in 1980. And so what they said, if you have a tree, so for this we only look on tree, so I want to label the vertices of the tree by elements of some group, and I call such labeling a harmonious labeling, that if I compute the sum along the edges, all sums are distinct. Okay? Right? So you want to assign elements of the group to the vertices such that all n minus 1, so the tree on n vertices always have n minus 1 edges, so all these sums are distinct. Now, of course, how small should be this group? This group should be of size, at least size of the 3 minus 1, because there are n minus 1 distinct numbers you want to get. And so the famous conjecture of Graham and Sloan says that you almost can get it always. So if you take an arbitrary tree on n vertices, you always have harmonious labeling by the numbers from 1 up to n. Right? So you can assign numbers from 1 up to n, addition mod n, such that the numbers are distinct. Observe that this is quite a non-trivial statement, because the number of potential trees on n vertices is super exponential. It's n to the power n minus 2. And for each of them, for each of these trees, you want to prove this result. So here's an, for example of this thing, right? So if I take this tree and assign these labels and compute some modulo 7, right, then I get the distinct numbers. Is this concept clear? Right, so you assign. Now, what we know about this conjecture? So people verify this conjecture for some very simple trees, like paths or stars, right? So path is just, right, so this is a path, this is a star, right? So very simple trees. So there are, I think, examples where maybe minus 1, it does not suffice. Yeah, so that's why you have that. But actually, let me say, it's a very good question. So for this conjecture, it was not even known that if you give me 1 plus epsilon times n labels, a little bit more than I need, that I can do this. So this result was proved only for trees with bounded degree. So observe that, for example, star has very big degree. But if you tell me that your tree has only degree up to 10, then this asymptotic result, not a precise result, with n plus little of n labels was known. Right? So why this is related to this finding rainbow trees? Because what we can do, we can take a Cayley sum coloring of the complete graph. So indeed, let's take the edge coloring of the complete graph, where we color the edge x plus xy by the color x plus y modulo n. Right? Just take n vertices and color by their sum. And now observe that, so this is the coloring. For example, 1 and 2 is 3, 7 plus 3 is 3, 6 plus 4 is 3. So therefore, all these edges I color blue, and I'll do it for all the numbers. So I get a proper edge coloring of the complete graph, right? Using precisely n minus 1 colors. And if in this proper edge coloring I find my tree rainbow, so here's a tree, for example, I want to find. If I find this tree rainbow, this is this tree, right? You can observe that this is precisely this tree, right? So then, if I look on this embedding, it will tell me the assignment of the labels, right? So I would know that this vertex I want label 2, this vertex I want label 3, this vertex I want label 4, this vertex I want label 7, 6, and so on. The fact that the tree was rainbow will exactly give me different labels on the edges. Okay, so this is one motivation. But let me, right, I want to maybe mention another motivation. Even more surprising motivation is the following question from the other area, which called graph packing, right? So what is this conjecture? It's a conjecture from 60s by Ringel, which says that if you have a complete graph on 2n minus 1 vertices, and you give me an arbitrary t, again, your favorite t, one of these many exponentially many trees, which have n vertices, then you can tile your complete graph by copies of this tree. So which means I can place the copies such that they're edge disjoint and they cover all the edges. Okay? So first of all, let's do sanity check. The number of edges in the complete graph on 2n minus 1 vertices, it's exactly 2n minus 1 times 2n minus 2 divided by 2, which is 2n minus 1 times n minus 1. Now, 3 on n vertices, right, has n minus 1 edges. So potentially, indeed, at least from the numerology, this is possible to place arbitrary t exactly 2n minus 1 times to cover the complete graph, right? So for example, I will demonstrate. So this is a path of length 2. This is graph on 5 vertices. And indeed, I can tile the edges of this graph using the path of length 2. But of course, this is a baby example, right? So what we know about this conjecture, right? So this conjecture again true for very special tree, paths, stars, and etc. And there is a remarkable result in this direction actually proved by several people, including Felix, which says that this conjecture is true for a very large class of trees which have bounded degree. So if you tell me that your tree has bounded degree, arbitrary tree, but then there is a bound on the degree of the vertices, and this conjecture is true. Okay. So very nice. It's a packing conjecture. No colors are involved. How this is related to what I'm talking about? So the reason that it's related that you can kind of phrase this conjecture about in a language of finding rainbow trees in some coloring of graphs. So what I do, you take your 2n minus 1 vertices and you put it on the circle. So this is your vertices of your complete graph. And then you color the edges of this complete graph by Euclidean distance between the points. So for example, the vertices which are distance 1 of the circle, you color green. The distances which are color 2 on the circle, you color blue. The distances which are color 3 on the circle, you color black. And the distances which are color 4 on the circle, you color red. So here you have 9 vertices, so you get 4 colors, right, which is exactly correct, which is exactly n minus 1, right? So on the circle with 2n plus 1 minus 1 vertices, because you take as short as distance, there would be only n minus 1 distinct distances, right? So again, you put your vertices on the circle, and then you color by the distance, right? And you get a color. Now observe that this coloring is two-bounded coloring. At every vertex, now it's not a proper, every color appears 2 times. And so here is your favorite tree, let's say, with 4 edges, 5 vertices. So imagine I took this coloring of the complete graph, right? Right, this is my coloring, and I find the copy of this tree, rainbow in this coloring. Just one copy. Then I claim that I can do tiling. And how I do tiling? I will take this tree which I found rainbow, and I start shifting it cyclically, clockwise, just by 1. So here is my first copy, then I shift it, and observe that I get a completely disjoint copy, because this copy will contain edges of all colors and different, and because of geometry of the colorings, this would be different edges, and again different edges, and again different edges, again different edges, and again different edges, and again, okay? So actually what I showed you that if in these two bounded coloring, you can find the copy of the tree which you want to tile the complete graph, rainbow, then you can tile, okay? And this motivated the following general result, which I proved with Richard Montgomery and Alexei Pokrovsky about 2020. So we showed you take any k-bounded coloring of the complete graph. So k doesn't need to be 1, 2, can be other numbers, but I had application for 1 and 2. You take any k-bounded coloring of the complete graph. You take any tree of size roughly n divided by k, a little bit less, tiny bit less. then in any k-bounded coloring of the complete graph, you can find your tree rainbow, right? So any tree, right, if it's only slightly smaller than n over k, then you can find it rainbow. So first of all, observe that it implies two previous conjectures asymptotically, right? Because if you k equals 1, it means that I can label every tree on 1 minus little of 1 n vertices using n labels in such a way that the labeling is harmonious. And similarly, if I take this distance coloring, I can find a tree of size roughly n over 2, slightly smaller than, right, we had 2n minus 1 vertices, roughly, slightly smaller than n. I can find it rainbow, and therefore I can tile almost all the edges. So moreover, observe that n over k is tight, because if I have k-bounded coloring, then at every vertex, every color indeed can appear k times, and therefore in total there would be n over k distinct colors, so I cannot improve it. So I want to say that the proof is quite interesting, but I will not go into it. It uses extensively probabilistic arguments. And as I said, another thing which I want to mention, this error term is necessary for such a general result, right? So there are examples where we cannot avoid it. It's not a Ringel's conjecture, it's not Graham's long conjecture, but there are examples where this little of n needed, okay? So I guess, looking on the time, I guess it's a good point maybe to stop my talk. There are many more things I can tell you about rainbow colorings of graph, but I think you suffer enough. So thank you for your attention.
Yeah, thank you very much indeed for that great talk. Are there further questions and comments? Yeah, Peter.
Probabilistic methods.
Right. So actually, I can say.
Let me just repeat the question in order to have it recorded. So the question was whether you could please comment on the probabilistic method.
Yeah. So the thing is, so the idea is to embed the pieces of the tree randomly. And one interesting thing you observe, and this may be right, just a cute result to say. So imagine you have a complete graph, say, which is properly colored arbitrarily, right? And now I take every color class and I choose it with probability half, right? So you would expect, right, that at every vertex, because at every vertex edges are distinct color, every edge I will choose it with probability half. So locally, I indeed behave like a random graph GN1/2. So I will behave like a random subgraph of complete graph. Now, but globally, because I'm picking every color class and not in every edge, I pick at every matching, so I should have certain dependencies. The question is, can I show that the graph which I get is really behave like a random graph GN1/2, despite that I have certain dependencies? And indeed, this is true. So one can show that if you have a proper edge coloring, regardless what the properties of your coloring, if you pick every color class, right, you keep the dependencies. At random, say with probability half or 1/3 or 1/10, you get a graph which in all relevant properties resembles the random graph G and P, where P is a probability. And that's very useful. So you can because what you will do, you can choose some random colors, right? And get a random graph. And random graph is very good expander, has many marvelous properties. And you're only using these colors. And you can do it again. You can use some other colors for something else and so on. So you can slowly build your tree. And that's what we're using, one of the things, right? The fact that if you sample the whole color classes, not a single edge, with probability p, it would behave like a random graph with appropriate edge density.
Further comments or questions? Yeah, Peter? Yeah.
That's okay.
Sure.
Several times results were proved if the edge degree of the tree, for instance, is bounded.
The degree of the tree.
How does that help if I know that? Is this
So you see, is especially because lots of proofs are probabilistic, right? So when you embed certain vertices, right, you should always look ahead where you embed future, right? So because you need to embed trees, so for example, if I already embedded this and this vertex, I should remember that in the future this vertex come and it's better be connected to this two, and it's better be connected by the edges of different color. Now, right, so your embedding is in stages. Now, if your degree is unbounded, if at some point you need to embed a vertex of very large degree, suddenly it puts a lot of restriction on your structure. And then it's very hard to work with such trees. So that was a bottleneck.
Further questions? Yeah, please.
I was interested in the transversal composition of the Latin squares. Can you see why it's not possible for n equals 6?
So there is a simple proof. You can Google it, so I don't remember on the top of my head. So the first proof was not that simple, but by now there are really simple proofs which show that n equals 6 is not possible, but everything else is possible. Actually, there is another very recent result which was mentioning of Richard, which is quite an amazing result, which shows that Euler was actually very wrong. So these guys, of course, he conjectured that if you 4n plus 2, then it does not exist. It does not exist only for 6, for all other things it exists. But what Richard with his course are showing is that if you take a random Latin square, right, which you basically look on all possible Latin n by n squares and you pick one at random, right? It's a difficult distribution to work with because the space is not so well defined, but there are lots of Latin squares. Then he can show that actually random Latin square for large n is always decomposable into disjoint transversals. So basically, right, if Euler had this access to like modern day computers, he would disprove his conjecture like that, right? Random Latin squares are always decomposable. But for 6, you need to do a specific proof.
Possibly I could comment, often this is just an arithmetic obstruction often. Similarly, why the multiplication table of set 2n has no transversal is also because you can do some equation and then you see, okay, this doesn't add up
but
to
for
0.
6, it's a bit harder because it's, I don't insist that it comes from group, right? It's a bit more case analysis. Yeah. I mean, after all, Euler didn't do it. He was a clever guy.
Yeah. Good. Further questions? This doesn't seem to be the case. So thank you very much again.
Thank you for having me.
Thank you for coming. So when is the next talk, Johannes, our next colloquium?